All right, so we've talked about double replacement reactions and what happens when they result in a new solid being formed, and that was the precipitation reactions. Now we're going to talk about another type of double replacement reactions, and that is called a neutralization reaction, and that's when you mix an acid and a base together. All right, so the formal definition that we'll be using for an acid is any compound that upon reacting in an aqueous solution produces a hydrogen ion, which is also called a proton. For right this moment in time, the baby definition is anything that starts with an H. And a base, by the Bronsted-Lowry definition, is any compound upon reacting in an aqueous solution that accepts that hydrogen ion or a proton. Right this moment in time, that's anything that ends in OH. So we're back to middle school definitions of an acid and base, and that will work just fine for right now. Okay. So a neutralization reaction occurs when an acid and a base are mixed. The products are always a salt and water. Some people think that salt is only NaCl, and in the example I'm going to give you, it is NaCl. A salt is defined as any ionic compound that has a cation and anion. We have the salt and water. A proton is given from the acid and received by the base to make water. So here we have a strong acid, HCl, hydrochloric acid, mixes with sodium hydroxide. This double replacement reaction has the cation ions changing places. So sodium is now paired with the chlorine, and the OH is paired with the hydrogen ion. The net ionic equation for a strong acid and a strong base will be the hydrogen ion, the hydroxide ion, making water. To look at that, we know that a strong acid ionizes completely, so it is a proton plus the chloride ion, and the Na plus ion plus the hydroxide ion results in sodium chloride, which is an aqueous solution, so it ionizes completely. And the other thing that's produced is water, which is a pure liquid and does not ionize. So the spectators here would be these, leaving us with this net ionic equation. All right, in a minute I'm going to show you a titration video, how to do an acid-base titration. When you do an acid-base titration, you rely on this fact, that at the end point, and you remember this from Chem 1, the end point is when the color change occurs. We want that end point when we design the experiment, so it's very close to the equivalence point. The equivalence point is when the moles of acid are equal to the moles of base. Okay, that's where we stop, when the moles of acid are equal to the moles of base, and that is the equivalence point to our titration. That is the complete neutralization of the acid and the base. Are we clear there? Now we can do some calculations to see where that should be and how much acid and how much base are necessary to achieve this complete neutralization, and we're going to, for this moment in time, use this equation. This is very elemental, and we will get far more sophisticated later. But for right now, the molarity of the acid times the liter of the acid used times the number of protons it furnishes in solution will equal the molarity of the base times the liters of the base times the number of hydroxide ions it produces at the equivalence point, or when it's totally neutralized. Okay? So that brings us to this problem. What volume of a 0.1 molar HCl solution is needed to neutralize 25 milliliters of a 0.350 molar solution of NaOH? First thing we should do is write a balanced equation hydrochloric acid plus sodium hydroxide will result in the salt, NaCl, and the water. All right, we can jump right into this equation. The molarity of the acid is 0.1 molar. We would like to know how much of it is necessary to neutralize the base. HCl furnishes 1 proton. And our base is 0.350 molar. It is 0.025 liters solution, and it furnishes 1 OH. Solving for X, we see that 87.5 milliliters of the acid was required to neutralize the base. Oh, if everything was that easy, we would be happy campers. Okay. Moving on to the second problem. In a certain experiment, 28 milliliters of 0.25 molar nitric acid and 53 milliliters of 0.320 molar KOH are mixed. Calculate the amount of water formed in the resulting reaction, and what's the concentration of either the H plus or the OH minus in excess after the reaction goes to completion. You should look at this and think, I know how to do this. This is a limiting reaction problem, and I'm good to go. Are you good to go? Instead of using mass ratios to figure out this limiting reaction problem, we're going to use mole ratios. But before we do any of that, we're going to write the balanced equation. So my balanced equation has nitric acid reacting with potassium hydroxide, and that forms the potassium nitrate and water. This is balanced. So I'm ready to do my limiting reactant problem. I'm going to be using mole ratios. And my mole ratios are taken from the coefficients of the balanced equation, 1, 1, 1, and 1. I'm going to figure out the number of moles of water formed. They don't ask us the number of grams. They don't ask us the concentration, so I feel like we can just leave this in the number of moles of water formed. We need to know what we're given in terms of moles for the acid and the base. To do that, we're going to take use of our calculation. We know that moles are equal to the molarity times the volume in liters. So the moles of nitric acid are equal to 0.250 times 0.028, and that is 0.007 moles of the nitric acid. We start out with 0.320 molar KOH, and we have 0.053 liters, and that is 0.0170 moles of KOH. So now we can put that into our problem. And we're ready to do our limiting reaction problem. I'm going to first test the HNO3. If I use all 0.007 moles of HNO3, how many moles of water will that produce? Yep, we can do this math. Over its mole ratio, we know that from the nitric acid, we can make 0.007 moles of water. Testing my KOH, if I use all of the KOH, how many moles of water will be formed. Mole ratio is 1. I see that I can make 0.0170 moles of water from the KOH. So right now I can see that HNO3 limits, and I can answer how much water is formed. This much water is formed. And I'm on to the second part of this question. What's the concentration of hydrogen ions in excess, as we know that the H limited? So how many hydrogen ions are left over? Well, we do know this. We know that some of the KOH was used to make the water. So we would like to know how many moles of KOH are equal to the 0.007 mole, or in the 0.007 moles of water that was made. We know that 0.007 moles of the KOH was necessary to make 0.007 moles of water. That's gone, tied up in the water. We started out initially with 0.017 moles of KOH. Unavailable, used up, are 0.007 moles. That's in the water. So left over, we have 0.01 moles of KOH left over. They asked us in the question, what is the concentration of the hydroxide ions? Concentration is always given in terms of molarity. So that would be the moles of the KOH over the liters of solution. Please visualize the solution. How much is it? What's the volume of the solution?
81 milliliters.
Okay. They took two volumes. They took the acid that had 28 milliliters and the base that had 53 milliliters, and they put them together. So the volume of the solution is 0.081 liters, and that gives you 0.213 molar KOH.
There's a, let's just say there's like a 2 in front of the H and a 3 for the mole ratio.
Okay, so H2SO4?
Would it be, the mole ratio be 2?
Yes. Well, I would have had to balance the equation differently. It would have made a difference in the problem up top, not the problem in the bottom. But for these right this moment, I'm not going to be doing those. Those come later. Right, this is